the second part of our little series about base quantities and derived quantities and homogeneity equations. If you haven't seen the first part, there should be a link up top, and go and have a look at that. This time we're going to discuss derived quantities, and as their name suggests, they come from a combination of base quantities or a combination of base and other derived quantities. Now, how we're going to build these up, we're going to discuss right now. So, derived quantities are formed by either multiplying or dividing base quantities. And let me explain this very quickly. May I remind you to be filling out those blanks that you see there. You've got them on your notes, okay? We're still on page 17 here. So, if you just take, for example, let's take, again, same example as we did before. Let's take velocity, okay? Now, velocity is given by distance divided by time, or displacement divided by time. So essentially what we've got there is a length being divided by time, okay? We can have another situation, say acceleration, okay? Acceleration is yet another derived quantity. How do I know that it is a derived quantity? It is not within that list of 7 base quantities. Okay, so that is why in the previous video I said those 7 base quantities you need to learn off by heart. Okay, so then when you see something different to them, then you'll know that it's a derived quantity. Okay, so acceleration is made up from, it's given by change in velocity over time. So it's made up by using velocity and dividing that by time. Now, if we take a good look at this, velocity, we've just said that it's a derived quantity. It's not a base quantity, okay? But we're dividing this newly formed quantity, this derived quantity, by a base quantity, okay? And this is another situation where dividing 2 quantities will give you a new quantity. Let's just take an example where we're multiplying quantities, say in the case of energy, specifically potential energy, or gravitational potential energy, that would be given by multiplying the mass to the acceleration due to gravity and multiplying that to height, okay? So we've got a mass, an acceleration, and a length. Both mass and length are base quantities, they happen to be base quantities, but we're multiplying those to get another derived quantity. Okay, so it doesn't really matter whether we're multiplying or dividing, or whether we're multiplying or dividing base quantities only, or base quantities to derived quantities, whatever. Okay, so the process of multiplication and dividing gives you a possibility of combining or creating new quantities. In all of those cases, we'll call those quantities derived quantities because they were derived from other quantities, a combination of other quantities. Now, is it possible to create derived quantities by adding or subtracting? And the short answer to that is no, okay? The explanation I'd rather give there would be if I've got, say, I first move through 5 meters, okay? And then, stop, take a break, move on another 2 meters in the same direction. Okay, so essentially the length that I moved through is a total of 7 meters. Please understand what's going on here. What are we doing here? We're trying to add a length to another length. Would that give me a new different quantity? No, the answer to it is still a value for length. Okay, so by adding 2 quantities, or rather 2 values of that quantity, we'll still end up with an answer for that same quantity. One thing to note, can we add 2 different quantities, length, for example, and mass? Had this been 2 kilograms? No, we can't. We can multiply 2 different quantities, but we can't add 2 different quantities. So in that particular case, you will not be able to work that out. So addition can't be used to combine quantities to create new quantities, and same thing goes for subtraction. If we're just trying to subtract different quantities, You can't, if we're subtracting the same quantity, well, you can do that, but the answer would still be that same quantity. All right, so the only way to combine new quantities to create derived quantities is by actually multiplying or dividing quantities. Now, some derived quantities are given special names, okay? And let me just discuss this very, very quickly. One way to understand this is by understanding, or by understanding what certain special units represent. For example, let me take force. Force is measured in newtons, and it's simple as a capital N. But we're saying that any derived quantity, in this case I'm taking force, is created by combining two or more base quantities. Okay, and by combining quantities, whether they're base or not. So in this case, we should be able to break this down, the unit Newton, into base units. So let's start off with some very basic examples and move on to the quantity of force, and we'll see the process of breaking down their units into base units. So, starting off with something I've been repeating all along, velocity. It's made up of distance and time, length and time, both of which are base quantities. Okay, so if I am to just list down their units, the unit for distance is meters, the unit for time is seconds, and therefore the unit for velocity is meters per second. Because this is fairly easy to remember, it is not given a special name. Okay, it is left as base units, and obviously many times, I mean, when we're working with speed or velocity, we're always stating the units as meters per second. Let's go with something a bit more complex. Acceleration, which is the change in velocity on time. Now, this time round, as we said earlier, time is still a base quantity, so we can leave it as is, but velocity is not a base quantity, it's a derived quantity. So let's just try and open up that velocity. Let's try and understand what this was combined from. And velocity, as we had said before, is given by combining distance and time, by dividing them, but by combining them, both of them. So again, let's see what base units velocity has. We've done it already, I know, but this is the process you need to do in an exam. So let's see what this gives us as far as base units are concerned, and then we'll try to understand what the units of acceleration are, and where essentially we'll understand where they came from. Okay, so length or distance, its unit is meters. Time, that unit is seconds. Now, meters per second is the unit for velocity. So velocity here is in the numerator. Okay, so what that means is it's got the meters in the numerator. Okay, so it's got meters up top, and in the denominator next to the time, it's got the unit seconds. Now, obviously then this time, that t has seconds as its unit, and therefore combining these two, we'll end up with a meters per second squared. And that is the unit for acceleration, and it was also so simple, or rather simple enough, to be left as base units. Now let's move on to something a bit more complex, which is force. If we are going to move on to, say, force and choose an equation for it, mass times acceleration. So what the equation states is that we can get to force by combining these two quantities. We're multiplying mass times acceleration. Now, if we take a good look at this, mass is a base quantity, okay? So we can leave it as is, but acceleration is not. So what I suggest we'll do to find the base units describing force is to break down the derived quantities. And to do that, we need to choose an equation which is about acceleration in this case. Okay, so I'm moving on to the side here and listing down an equation for acceleration. Any equation will do. And go through the same process we did earlier. If I take a good look at this equation, then I know that this is a base quantity. So yeah, it can't be broken down further, so we need to leave it as is, but velocity is a derived quantity, so we can break that down further. And to do that, I need to choose an equation for velocity. Only to note that the building blocks, the building parts of velocity are both base, okay, base quantities. So we can't break those down further. And all we need to do then is start translating into units, okay? So let me remove this. So length, meters, time, seconds. That we take, that's the unit for velocity, okay? So we'll start writing it down in the numerator, and that means it's got seconds in the denominator, which happens to be next to the units for time there. Time has the unit seconds, so yep, that's going to give us meters per second squared. So that's the units for acceleration, we know that already, okay? So meters per second squared are the units for acceleration there, and we need to list down the unit for mass, which is the kilogram. So essentially we're saying that kilogram meter per second squared are the base units for force. Thing is, it is complex enough for us to not want to keep on writing all of these units down every time we need to calculate a force. Okay, so if we say 20 newtons, instead of writing newtons, we should be writing 20 kilogram meter per second squared. Imagine trying to work many calculations with this and trying to write this, these units down over and over again. And mind you, some of these units for derived quantities can get very, very, very complex. So that is why we're saying, listen, when you've got a complex set of base units for a derived quantity, they are many times given a special name. And in such a case, force is generally measured in newtons, but what we're showing here is what the unit of newtons actually means. It is the combination of mass, length, and time squared. Okay? Now, on our notes, and again on page 18 this time around, there's another table. You can start listing these down. Okay, so we've discussed already velocity, acceleration, and force. But I want to do another two derived quantities. Again, same process, breaking these down into their base units, because this is many times asked for in an exam. So we'll prepare you for that. If you want to pause the video and then just check the solution, try them on your own, check the solutions later, go ahead. I'm going to discuss them very, very quickly. I'm going to discuss the quantities of energy and power next. Okay, so going with energy. Choose any equation for that derived quantity. Okay, so if we're going with essentially what we're going to do is trying to come up with the base units for energy. We know that the unit, which has a special name, is called the joule. Okay, it's given by a capital J. But what does the joule represent in terms of base units? What is it made up of? So choose an equation for energy. Any equation will do. Kinetic energy, half mv squared, potential energy, mass times g times h, Einstein's equation, mc squared, they all work, okay? So I'm going to go with potential energy, okay? mgh. Now, looking at this, I've got mass, which is base, g, which is acceleration due to gravity acceleration being derived, okay? And h is just the length. Again, that's base. So we can leave the base quantities as they are, but we need to break down, we need to break down the acceleration further, okay? So tackling that first, we need to come up with an equation for acceleration, which we've been using as change in velocity on time. Again, time is base, velocity is not. So we need to break down velocity further. Choose another equation for it. Velocity is equal to displacement on time. Both of which are base quantities, so we can't break those down further, so we can start converting them into units. Units for distance, meters, units for time, seconds. Take that to velocity. meters numerator, seconds denominator next to the unit for time. Trying to keep same color combinations here just so you can follow better. Okay, so meters per second squared is the unit for acceleration, which I'm going to carry over to here. Okay, so I write it down just under the acceleration. So its units are the meters per second squared. These units are multiplied to the mass, so the units of kilograms, and to length, so its units would be meters. Since these are all multiplication, then the units are multiplied together as well, and we're going to end up with a kilogram, meters squared, all over seconds squared, and you can see that it is starting to get quite a bit more complex, and we've got a special name for it just to not keep on writing these down over and over again. Okay, one last example for us. Then you've got linked in the description the worksheet, which I encourage you to download and work out a couple of examples of these and compare your answers to the solutions I've provided. What we're going to cover next is power. Okay, power as an equation. I mean, you can use any equation that you want, but I'm going to go with power is equal to energy divided by time. Now, energy is not a base quantity, so we know that we need to break this down further, but time is, okay, a base quantity, so we can leave that as is. Energy, we need to choose any equation for energy, and I'm going to go with the same equations just to keep building one on top of the other. So I'm going to choose potential energy for it. You can choose whichever equation you'd like, okay? Doesn't really matter. The thing is, in an exam, you'll be given just one example, okay? So, or rather one question. So if you're asked for power, then you need to show what you're working. I know that these we've already worked them out. So do we need to keep on breaking this down if we've got the answer already? Well, if you've presented it in the same paper, you don't have to. Okay, you've already worked it out somewhere else in that same paper because we've already shown the examiner that you know how to work that out. But if this is just the first instance that you've come across this in an exam, then you need to show all your work. I'm not going to take any shortcuts here, and I'm going to show everything. So, again, same process, okay? So mass, base, quantity, we can't break that down further. G is acceleration, we have to break this down further, but H is also a base quantity. So simply breaking down acceleration there, changing velocity on time. Velocity is derived, time is not. So taking a different color here. And I'm breaking down velocity, which is distance on time. And that is where I need to stop, okay? Distance and time are both base. So now we start converting units, okay? Get used to this process, please, because this process will help you solve these during an exam, okay? So meters per second, that is the units for velocity. Next to that time there in the denominator, you've got the unit for, which happens to be the same in second as well, but for this value of t, okay, and not for that t. So that is why I'm trying to keep different colors here for you to be able to follow where things come from, where the units are coming from essentially. So meters per second squared, units for acceleration, which I'm going to write just underneath g, okay. So yeah, height, it's a length, okay, and since it's a length, it's got unit meters, mass, kilograms. We've already done these, so yeah, I'm just going through the different steps. Unit for energy, that's the joule essentially, okay? But that is the unit of this. So starting writing this off in the numerator, that means energy is kilogram meters squared in the numerator, and it is divided by seconds squared, and seconds squared happens to be next to this value of time. Okay, so the unit of this time is yet another second. Simplifying that, kilogram meters squared all over seconds cubed. Okay, so what the watt represents, watt being units, the unit of power, is essentially all of those units combined, kilogram meters squared divided by seconds cubed.